Welcome everyone to today's lecture. We stopped last week with the discussion of the factor models and the market models. We shortly talked about the capital asset pricing model and the market factor as part of a one factor model. We also talked about the extensions of this model, most notably by Fminunc, Carhart, and nowadays in the asset pricing literature you will find a huge amount of different factors that have been identified to drive the cross-section of stock returns. And the most famous ones are the market factor, aka the index, the market index. You have small minus big, high minus low, and in the Fminunc Carhart model, introduced by Carhart, the momentum factor, which is quite easily constructed. You simply take, if you have 100 stocks, you invest in the 100, let's say the 10 stocks that have performed best during the last year, and you short sell those 10 stocks that have performed worst last year. So you try to construct a portfolio that relies heavily on those stocks that have performed quite well in the past, that have momentum, and you finance this investment by short selling those stocks that definitely have no momentum, or rather negative momentum going down. So these are four types of factors you can include in a factor model. And I told you last week that we now want to extend this model even further by introducing the risk-free investment. You can take your money to the bank and you get risk-free interest rate on your money. So this is what we're trying to include in this model right now. So we have one risk-free investment, thus we have risk-free security return R0. This is not very realistic. Why is this not very realistic? It's not very realistic because usually you will have several risk-free investments. What are these? In modern markets, you usually have government bonds. If you are looking for a type of security, a type of investment that can be assumed to be risk-free, you will usually end up with government bonds issued by states that are assumed to be free of default risk. Now, even this is a slight oversimplification because I would have guessed 10 years ago, one would have said, okay, we can take US government bonds, we can take US treasury bills and assume that they are risk-free. Nowadays, with all the things going on in the modern world and in modern economies, I would assume that not even the US are completely free of default, because the US, every now and then they have a government shutdown, and nowadays I would say maybe we should use German government bonds to get an investment that is risk-free, but this is hypothetical. In any case, any state can go bankrupt. Any state can default, and one has seen this throughout history. So we'll take government bonds, and the next simplification is that even if we assume government bonds are risk-free, it might still be that you have different government bonds with different maturities and different coupon payments. This can be very easily seen if you just pull up a newspaper and look at the fixed income section of your newspaper. In German, this is called der Rentenmarkt. Why is it called der Rentenmarkt? In English, it's the bond market. The bond market meaning that it's the market for corporate and government bonds. Rentenmarkt in German reminds you that this is an investment for your as a sort of a life insurance. You can invest in these very risk-free fixed income products to save for your retirement. That's why it's called Rentenmarkt. Rentenpapiere. So it's a fixed income bond market. And the second simplification we have here is that you will have different bonds with different maturities and different interest rates and different coupon rates. So you do not simply have one, let's say a zero coupon, but you will have different bonds with different maturities. And so on. And what one would do now is one would need to estimate the yield curve, the term structure of interest rates, to identify the set of interest rates for different maturities. We'll see this at the very end of this lecture, and we'll see some methods that are used by central banks, how you can extract the term structure of interest rates from a set of given bonds. I'll just say this in German, das ist die Zinsstrukturkurve oder die Fristigkeitsstruktur der Zinssätze. Why do we need this? Well, you usually do not have one simple interest rate R0, but you will have R1, R2, R3, and so on for a maturity of 1, 2, 3 years. And this is a little bit more tricky than these models might make you think it is. Okay. So here, to simplify things, we have one risk-free interest rate. I'll get this away. We have one risk-free interest rate. The investor can borrow and invest any amount of cash in the risk-free investment. All investors only take the index's expectation value and variance into account. And A, that varies between 0 and infinity, is the part of the available amount of cash that is invested in a portfolio P. That is a possible portfolio. That is an element of the set of all possible and attainable portfolios. And 1 minus A is the part invested in the risk-free investment. So one could also say alpha% of our money is invested in the portfolio, and the rest goes into the risk-free investment. So the overall return is simply A times the return on the portfolio and 1 minus A times the risk-free rate. So this is the portfolio investment, and this is the risk-free investment. Very simple. Now for the whole portfolio, risky part and risk-free part, we have the following. The expected return is simply A times the expected return of the portfolio plus 1 minus A times the risk-free rate. So this can be simplified to this. We have the risk-free rate plus the percentage put into the portfolio times, what is this in brackets here? This is the excess return of the portfolio. That's the difference between the return on the portfolio and the risk-free rate. And later on, we would assume that this is some sort of a risk premium, because we would assume any investment should at least yield the risk-free rate. And if we have a risky portfolio, well, the return should be higher. And the difference, the residual between the portfolio return and the risk-free rate, can be considered a risk premium for bearing additional risk in contrast and in comparison to the risk-free investment. And the variance of the full portfolio is simply A squared times the portfolio variance. Why is that? If we were to do it strictly by the book, we would see that we would need R here is our new random variable. We need to calculate the variance of a random variable, and the random variable is given by a linear combination of two other variables, Rp and R0. Now here we can see that R0 is not stochastic, it's deterministic, so the variance of R0 is 0. And the general formula would be to calculate A squared times sigma P squared plus 1 minus A squared times sigma of R0 squared plus 2A 1 minus A times the covariance. But again, as the risk-free investment is deterministic and it's stochastic, this is 0, and this is the only part that is left. Quite simple. If we now take the second equation, rearrange it, and get A equals sigma divided by sigma P, and insert it into the equation, the definition of the portfolio return, the expected return of the portfolio, we get expected return on the full portfolio is equal to risk-free rate plus the expected return on the risky portfolio, on the market, on the index, minus risk-free rate divided by the portfolio standard deviation times the volatility. So if we have a constant portfolio P, and if we only vary the share A of the portfolio in our investment, we will get a straight line through R0 with this as the slope, Steigung. And this is what we call the Sharpe ratio. The Sharpe ratio is defined as the expected return on a portfolio minus the risk-free rate divided by the standard deviation, the volatility of the portfolio. And this is the Sharpe ratio, and this can be viewed as a risk adjustment performance measure. It gives you the expected return on your portfolio. You correct for the risk-free rate that any investment should give you, and then you take this excess return, expected excess return, and divide it by the risk you're taking. And then you can compare investments by their Sharpe ratios as one way of risk-adjusted performance measurement. And this is the Sharpe ratio. We can also compute a generalized Sharpe ratio, which is also called the information ratio. This is the expectation of Ri minus Rb if we take a benchmark, and again do the same here in the variance and the volatility. So we do not look at just one portfolio, but we compare our portfolio to a benchmark portfolio and then calculate the expected return and the variance. Difference is with the regular Sharpe ratio, this would be the risk-free investment. So as a benchmark, we would use the risk-free investment, but you can do the same with any other benchmark portfolio. This is the information ratio. If you plot this in a graph, you will get all those different possibilities in a mu sigma graph. Obviously, you will have the portfolio here, and this is the, let me just write this a little bit larger. This is sigma p, and this is mu p. So these are the expected return and the volatility of the return of the stock portfolio. And this is the risk-free investment. Obviously, here, the risk-free investment will have a risk of 0. The volatility will be 0. And then you can combine these 2 points with a line, and you will get this graph. For different portfolios, P1, P2, and P3 here, you will get different graphs if you link them with the risk-free investment. And what happens now? We have our efficient frontier. We know that if this is the minimum variance portfolio, this is the efficient frontier. We'll have the market portfolio, and what we can do now is we can choose any portfolio, not just the market portfolio, but we can take any portfolio that is possible, might be efficient, might not be efficient, and combine it with the risk-free investment. We will get different lines like this. But if you take any, let me just delete those again. If you take any point on such a line, for example, this point, this would be a combination, say, of this portfolio and the risk-free investment. Maybe even half. 50% risk-free investment, 50% this portfolio P, let's call it PX. Now, this is a combination of the risk-free investment and the stock portfolio, but still it is dominated by this point on the efficient frontier. So this should not be done. So yes, we can combine the risk-free investment and the stock portfolio, but why should we? Because we can still use this portfolio on the efficient frontier, and it would give us a higher expected return at the same price, at the same risk. And if you now do this over and over again, you will see that at some point you will get this line here. And you will get this point here. This is the tangent portfolio. And any point on this line is efficient, because, for example, if you take this point, you cannot take any portfolio on the efficient frontier that will dominate this point. If you take any point here, well, you can still use the minimum variance portfolio, but this portfolio here gives you the same expected return at a lower risk. So all these points on this line are efficient. How much would you invest in the stock portfolio? Well, you can see here that actually the stock portfolio is the same for all investors. You will always use this point here, and you only need to decide how much money and what percentage of your money do you want to put in your risk-free investment, and how much money will you put in your stock portfolio. If you have a point like this, you will invest, say, 200% in the stock portfolio, and you will borrow money. If you take this point here, you will have 50% or 60% risk-free investment and 40 or 50% in the stock portfolio. And this is the so-called two funds theorem or Tobin separation. What is separated? Now before, without the risk-free investment, we saw that actually we needed a utility function to decide what portfolio an investor would choose. We had different portfolios on the efficient frontier. They were all efficient. The question which portfolio is optimal for an investor depended on on his or her utility function. If you are risk averse, if you are risk friendly, if you're risk neutral, you will choose different portfolios on the efficient frontier. Now, as soon as the risk-free investment comes into play in this model, all investors will choose the same tangent portfolio on the efficient frontier. They will only differ in the amount of money, in the percentage they are investing in the stock portfolio, and how much money they will keep in the risk-free investment. If you're completely, infinitely risk averse, you will choose this point here. It will be on the tangent line. If you are risk friendlier, you will choose a point here or here or here, but all investors to some extent will invest in the risky tangent portfolio. Why is it called Tobin separation? You can separate two decisions, more or less, the consumption and the investment decision. The investment decision can now be delegated to a portfolio manager. Why? Everyone is buying the same portfolio, the tangent portfolio M here, or it's called T here. Everyone's buying the same portfolio. I will buy 50%, you will buy 10%, maybe you will buy 20%. Some of you will not buy any part of the tangent portfolio, but we are all buying the same portfolio. Meaning that we can all hire a portfolio manager to combine the assets to find the right tangent portfolio. And as it turns out, the tangent portfolio is a market portfolio. Meaning that all of this is the very foundation of passive fund management, of passive portfolio management. Why? What are passive portfolio managers trying? They are trying to rebuild the market index. You know what the difference between active and passive portfolio management is? Active portfolio management means you're trying to pick those stocks that are currently underperforming and you're trying to isolate those stocks with which you can earn money, and you can try to beat the market. Passive portfolio management, in contrast, does not try to beat the market. You simply try to track an index, and this is the theoretical foundation for it. The model tells you that in this very simple setting, you cannot beat the market. You can only try to combine the risk-free investment with the market portfolio, and your job as a portfolio manager is to take your customers' money and to track an index, to rebuild the market portfolio at a lower cost, at the lowest cost possible. Okay. So T is the tangential or tangent portfolio. It is optimal. You should choose a point anywhere on the line. It still depends on the risk preferences of your investor, but the risky share, the stock portfolio, is identical for all investors. The Sharpe ratio of the tangent portfolio is maximal, and this is the Tobin separation. So the separation of the optimal complete portfolio into an individual part invested in the risk-free investment and the risky part, stock portfolio. This is the two funds theorem, or the Tobin separation, the statement that the decision on the portfolio composition can be separated from an investor's risk attitude. Okay. Now, last but not least, we'll finally get to the capital asset pricing model. Now, as it already implies, or as the name already implies, the capital asset pricing model is a pricing model. We want not to explain returns. We do not want to explain the composition of a portfolio, but we want to price assets. We want to get a theoretical price for, say, a stock. So the assumptions, to summarize them, of the capital asset pricing model are: we have n risky securities, one risk-free investment. There are m investors with a budget each of VI. The whole market volume then is V, simply the sum of all the budgets VI. All investors have identical expectations toward the quantities risk-free investment rate, expected return, variance of the returns, and the covariances. This is obviously a very strong assumption, meaning that every investor knows everything, at least the decision-relevant variables, the expected returns, the volatilities, and the covariances. Usually not the case in a market. And when we start the model, the market is in equilibrium. Now, every investor buys an efficient portfolio PI, consisting of the tangent portfolio, which share lambda I, and the risk-free security. The demand portfolio of the market is then given by the sum overall investors from I equal to 1 through m, lambda I VI times xt, and this is the demand vector, xt1, xtn. Remember that we have n risky securities, so we need to know which securities every investor buys. So it could be that if you only buy the risk-free investment, could be just 1, 0, 0, 0, 0, 0, depending on the volume, but you can also spread your investments. On the other hand, we have a supply portfolio which consists of all available securities. This is the market portfolio, M. It's defined that every individual security is fixed towards the relative share PI divided by P of the complete market value. And the matching investment vector now is XM, meaning that this is XM. We have stocks available, they have prices. These prices exist still from T equal to 0 from the initial market equilibrium. And then we have the prices and the overall volume of the market. And this gives you the shares in the index. Now, as the supply portfolio, the number of shares is fixed. And this is not endogenous to the model. This supply portfolio is strictly determined. It follows that in equilibrium we have sum of overall investors, lambda I times VI times XT, that is the amount of money invested in the portfolios, the demand vector and the total demand, has to equal what? The supply vector xm times the market volume. And this gives you the equilibrium. So demand equals supply. And the consequence of this is that xt and xm must have the same shape, must have the same form, so they are identical. xt and xm are identical, and this gives you this, that if you sum up the budgets of all investors, the total budget of all investors should be equal to the market cap. In equilibrium, this means that T equals M, the tangent portfolio is the market portfolio. This is the important result here, that in the capital asset pricing model, the tangent portfolio is the market portfolio. And this is why in most textbooks, as a one-factor model, you will always start with the capital asset pricing model and the market portfolio or market index as the sole factor driving the cross-section of stock returns. So the tangent portfolio is identical to the market portfolio, and from this very basic finding you can derive some central consequences. First of all, the set of all optimal portfolios is given by this equation here. You will start with the risk-free investment plus the Sharpe ratio times the volatility. This, if you plot this in a mu sigma graph, as we've done before, this is called the capital market line, Kapitalmarktlinie. The market portfolio again has a maximum Sharpe ratio. Only portfolios that duplicate the market portfolio in their risky part are optimal for an investor, and this is again the foundation for passive portfolio management or indexing or index tracking. Moreover, we get the same here for the expected return if instead of the Sharpe ratio we use the beta factor. You can simply rewrite it as risk-free investment plus the beta factor times the excess market return. And this, again, if you draw this in a graph, this is called the security market line. So the capital market line here in a mu sigma graph, and the security market line if you draw it up in a beta factor and mu coordinate system. The interesting idea now here is, if you take any investment, if you take any security in the market, and if you think that it is here or here, this means that it is over or underpriced. The price and the expected return is too high or too low for the stock to be efficient. And if the market is efficient, the price should go up or down. And this again is the idea behind active portfolio management, that you identify, or you try to identify, those stocks that have a price that is currently too high or too low to be true in an efficient market, and you buy or sell these stocks, and you try to beat the market, and you speculate that prices will go up or go down back to the security and capital market line. Okay. We've seen the beta factor. You probably know that it measures the sensitivity of the individual return towards changes in the market return. If we rearrange it a little bit, you get this. Expected return minus risk-free rate equals beta factor times the excess return on the market portfolio. Meaning that on the left-hand side you have the excess return on an individual stock, and this is given by the beta factor times the excess return on the market portfolio. Okay, and this is the interpretation here. The return is the risk-free investment plus the market price of risk times the systematic risk of the investment. And finally, if you combine all this, initially we were interested in pricing a security. Now this is very simple. the pricing function and the prices in equilibrium are simply given by the price P equals the expected investment, the expected cash flow, divided by 1 plus risk-free investment, plus again the beta factor times the excess return on the market. So this means the price of the portfolio, or simple also security, corresponds to the expected return V discounted at the risk-free rate corrected by risk premium. In the end, you will get a pricing formula that tells you that you need to take the future cash flows and do not simply discount with the risk-free rate, but you discount the future cash flows, the expected cash flows, by a risk-adjusted interest rate. And this risk-adjusted interest rate consists of the risk-free rate plus a risk premium, and the risk premium now is given by the systematic risk, the investment, the portfolio the security has towards the market portfolio. And this is given here by the beta factor times the excess return on the market portfolio. So that's the capital asset pricing model. You might have seen this in a lecture by Professor Schumacher. If you are interested, I told you this, if you're interested in this in more detail, I can only advise you to take up the textbook by John Cochran on asset pricing. It's very well written, and it starts with the very basics. With the simple idea that asset pricing for any asset and in any market is actually quite simple. You need to take the future cash flows and you need what is called a pricing kernel. You need to get the discount factors. The risk-free rate is usually given, and the question then only is how to find the set of interest rates and the set of risk premia taken from all investors that causes prices to be in equilibrium. And then you can start up with asset pricing. Okay. Now, we've talked about portfolio optimization, portfolio theory from a theoretical standpoint. Now let's turn to the more practical question of how we can optimize such a portfolio. We'll see this later on, but I want to start with some general remarks on optimization. If you take up, say, R or MATLAB or Octave, there are a bunch of ready-to-use optimizers. Even in Excel, you have an optimizer function, which you can supply and provide with a function to minimize or maximize. And you've already done this in school. You've already, in high school, calculated the maximal points or the minima of a one-dimensional function in the real numbers. But we want to do this now a little bit more in a more sophisticated way. We start with the optimization problem that we want to minimize a one-dimensional, oh no, it's not a one-dimensional function, but it's a function that has a one-dimensional output, but a multi-dimensional input. Why is this important? You've probably taken the math class here in Leipzig. I'm not so sure how far our colleagues from the math department go when it comes to real multidimensional real analysis and real calculus. Just think about this the following way. You can look at a function from R to R. This is usually what you do in high school. You can also look at a function, what we are doing now, from the Rn through to R. But obviously you also might have functions that look like this. You will have input data from the n-dimensional real space, and you have a function output, function values in the m-dimensional real numbers. Now we are not looking at this here, but obviously we are taking up this case here, and this is already done at high school and also in first year, bachelor. So we want to minimize a function in an n-dimensional real vector under the condition that x is admissible. It might be that we have very strong constraints on x. It might be that we do not have any constraints. But the vector x should be an element of the solution space S, and S is a subset of the n-dimensional real numbers. So it's a scalar valued function, and we have a decision variable x. Now, first, note that we will only deal with minimization problems. Why? And by the way, R and MATLAB and any math program will only offer you a function minimizer. Why is that? If you want to maximize a function, you can simply do the following. Instead of maximizing a function f with respect to x, you take the minimum, the negative of the minimum of minus f. This is equivalent. So you can transform any maximization problem into a minimization problem, and then you only need one type of optimizer in your computer system. And by convention, usually you have a function minimizer. Now, the solution of such an optimization problem includes searching for a global minimum for which this holds. The function value of x star is smaller than any other function value for any other solution x in S. We want to minimize f. So if we find x star, a solution x star for which the function takes its minimum, that's our solution x star. Now, it might be that this is a global optimum, that is a global minimum. It might be that the problem is unbounded, meaning that it goes down to minus infinity. It could also be that the solution set is completely empty, that we do not have any solution. It might also be the case. And regularly, it might also happen that we have the case we've already seen in one dimension, that we have one local minimum here, one local minimum here, a global minimum here, and our optimization runs into a local minimum. Okay. To exemplify this, very simple, very small example, G is at x polyval and a vector 1 minus 10.5, 39, and so on, x. What is this? First of all, remember that this here is what is called in MATLAB code a function handler. It means that we want to define a function g of x. And to do this, we define g. We have to write at. In brackets, we now include the variable that is provided to the function, so that is x. And everything that now follows is the definition of the function g of x. And in this case, it's polyval. That's the value of a polynomial. And polyval has two ingredients, a and b. A is a vector for the coefficients of the polynomial, and b is the value at which we want to evaluate the polynomial. So this here gives you 30 minus 59.5x plus 39x squared minus 10.5x to the third plus x to the fourth. So this is a very simple polynomial. And we've just defined g as this polynomial. X vet is what? It's simply a vector of numbers between 1 and 4 in steps of 0.05. So it starts with 1, 1.05, 1.1, 1.15, and so on. And then we plot the function at these points. Why do you need to do this? Quite simple. Now, remember that a computer in its very nature is quite stupid. A computer cannot do anything, it can always do less usually, only some things faster than a human brain. And if you want to draw a function, what would you do? Even a linear function with 2 points, how can I draw this line? And how can I draw this function? In our minds, we will say, okay, these 2 dots should be connected at these points, and then we draw such a line. Now, with a line graph, this is very simple. But if I were to tell you, well, you need to draw a polynomial of, say, x squared, how would you draw this? Well, just like the human mind and the brain, the computer will draw adding points and points somewhere in between, and it will only increase the number of points. And then for the human eye, it will look like a line. And this is the same that is done here. I'll say this in German because this is a little bit tricky. Auch ein Computer, genauso wie wir, können ja keine Funktion einfach aus dem Stegreif zeichnen. Das, was wir nur machen können, ist, wir können Funktionswerte auswerten, Werte berechnen und die dann eintragen. Und wir machen das schon bei einer einfachen Linie so. Ja, wenn ich Ihnen jetzt sage, zeichnen Sie doch mal 5x minus 23x Quadrat, das können Sie ja auch nicht aus dem Kopf und wissen, das muss so aussehen, sondern was Sie machen würden ist, genauso wie der Computer, Sie wählen genügend Zahlen aus, setzen die in die Funktionen ein, tragen die Zahlenwerte, die Funktionswerte ein und dann ergibt sich für Sie irgendwie ein Muster und dann verbinden Sie die Punkte. Und der Computer macht letztlich sowas Ähnliches, der zeichnet einfach viel mehr Punkte. Deswegen in der Linie 3 plotten wir jetzt diese Funktion, indem wir einfach ausreichend viele x-Werte nehmen und die dann entsprechend dann die Funktion an diesen x-Werten auswerten. This is the result on the next slide. And as you can see, this is the plot with of a polynomial with 2 optima, one local, one global. Okay. Now in MATLAB, you can use Fminunc for unconstrained function minimization. That's why it's Fminunc. Function minimization unconstrained, also ohne Nebenbedingung. And we use this by calling Fminunc G, and we'll start at 0. That's the starting value. And the results are written into x and fval. Why do we have 2 outputs? X star, and we also want f of x star. We want x star, the optimal solution, but we also want the function value at the optimal solution. And as you can see, the result of Fminunc is 1.48, and this is this global minimum. But we started at 0 here. So if we choose a different starting value, you can see we start at 5. Fminunc will give you the result 3.64. This is this point here. And this is a very simple observation. Fminunc is the standard optimizer in MATLAB. And it's heavily tuned. This is not a very simple algorithm, but it's a set of algorithms that is tuned to the max. And it's a very, very simple function to minimize. It's a polynomial. And even with this very simple polynomial, depending on the starting value, the algorithm will run into a local optimum. So don't expect too much of these functions. Now, a function can also have several global optima. And this is a second example. This is again a polynomial, and you can see We have two global minima. Neither the left or the right one is better. Both give you the same function value, and both are optimal. And then, obviously, it depends on the starting value. Now, in mathematics, in numerical analysis, we also sometimes have infinite dimensional problems, meaning that the dimension of the vector x is not fixed. We only have seen so far one-dimensional examples, and we are now dealing with n-dimensional solutions. But in mathematics, you will also sometimes have infinite dimensional problems. So you have an infinite number of decision variables. We will not deal with these here. But if you are wondering what mathematicians are nowadays researching, a couple of houses next to our building, then infinite dimensional optimization is one area of research. And you might encounter this in physics and mathematical physics sometimes. We can also differentiate between optimization with and without constraints. Without constraints, it's quite clear. You have a function f. With constraints, things get a little bit tricky. Why is that? If I were to give you this function, x squared, you know this from school, and you know this is a very simple case. In theory, you can show that if such a function fulfills some requirements, you can easily find the global optima. How do you do this? Well, you take the first derivative and set it to 0, and you know this is a critical point where you can check for a global optimum. Now, we can generalize, and we will generalize this result, that you can use derivatives and gradients of the function to find those critical points where you might find a global optimum of the function. The problem now is, with constraints, if, for example, we are interested in the maximum, things immediately change. What can happen is, if I say, well, I have a constraint saying that x, this is 5, x should be larger than 5. This means that suddenly we only need to check this area here. And this makes it quite difficult, because all our theoretical results on how the derivatives and how the gradients of the function should look like, we can put all those results into the garbage bin, because now we have to check this point here. And nothing special about this point. The first derivative is not 0 at this point. We know nothing about this point, only that it lies on the edge of the solution space, because this is where the constraint cuts off all the remaining points. And this is why constraint optimization is much harder and much more difficult than unconstrained optimization. Unconstrained optimization, you can do this in school, check for the derivative, and then you get the critical points. But with constraint optimization, it will most likely be that the solution will be on the border of the solution space, and we will need different methods for this. Convex versus non-convex optimization. We still need to talk about the question when a local optimum is also a global one. And with convex functions, this is quite simple. If we have a target function, an objective function f, if f is convex and the permitted solution set is convex too, we will call it a convex problem. If f is convex but the solution set is concave, we will call it a concave problem. And we get two very simple results. In a convex problem, a local optimum is always a global optimum. And in a concave problem, the global optimum lies on the edge of the solution set. So if you can check for the convexity of your target on your objective function, then you already know that you only need to find the one global optimum, because any local optimum will be the global optimum. Okay. This is also why you might have seen this in economics, in theoretical models. It's always nice to check for the convexity of a target, of an objective function. If you can show that the objective function is convex and you calculate one optimum, you know that it's the only unique global optimum. Now, for convex functions in the real numbers, obviously, optimization without constraints is quite easy. We have the following theorem. If the objective function is convex and differentiable on the n-dimensional real numbers, f will have a global minimum in the vector x star if and only if we have that the gradient of x at x star is 0. That is, all the partial derivatives with respect to x1, x2, and so on, they are all 0 for all indexes 1 through n. Now remember that in multidimensional real calculus, there is a fine distinction between the first derivative of a multidimensional function and the gradient. You can always calculate the gradient in the sense that you take the partial derivatives, and if you put the partial derivatives into a vector, it's called a gradient. And only, well, in most cases, but in some circumstances, you will not have a first derivative. The function will not be differentiable, but in most cases, the gradient will also be the first derivative, if I'm not very much mistaken. In German. Das ist der Gradient, das ist der Vektor der partiellen Ableitung. Aber Sie haben das vielleicht in der Mathematik gelernt, in der mehrdimensionalen reellen Analysis, dass die Ableitung nicht immer zwangsläufig leicht im Gradienten sein muss. Also in den Fällen, die wir hier betrachten, ja, alles schön linear, maximal irgendwie ein Polynom, reell sowieso alles, ist der Gradient natürlich die Ableitung, die erste Ableitung. Aber es gibt da bestimmte Fälle, wo dann Ableitung und Gradient nicht übereinstimmen. Und der Gradient ist in dem Fall hier wirklich einfach nur der Vektor der partiellen Ableitung. Und partielle Ableitung dürfte jedem klar sein. Also einfach die mehrdimensionale Funktion nehmen, nach einer Variablen ableiten und die anderen als konstant ansehen. Okay. Now, we can also differentiate between linear and nonlinear optimization. If the objective function is linear, things are quite easy. So a finite dimensional problem of optimization will be called linear if the objective function as well as all constraints are affine linear functions. Now if you have studied the bachelor's degree here at Leipzig, you will probably know this. This is not standard curriculum at all German universities, at least in case someone not from the math department does the math lectures. Usually in economics and business, we are quite quick to describe functions as linear. However, most economists have no clue about the fine definition of linearity in linear algebra. Linear algebra and the definition of linear space means that any mathematical space of mathematical objects for which you can define a linear addition, a linear sum, and a scalar multiplication is a linear space, meaning that if you have a times the function of a vector is the function of a times the vector v, and if the sum of two vectors is the sum of the function values of those two vectors, any mathematical space that fulfills these two requirements is a linear space, is a vector space. And then the function f is linear, any function that fulfills these requirements. Now, from this you can see that a function f of x equal to a plus b times x, something every economist would immediately consider to be a linear function, is not a linear function in this strict sense. Why? Because with this definition of linear functions from linear algebra, any function has to go through the 0. And if you have a not equal to 0, then a plus bx is not a linear function. But this is called affine linear in mathematics, affine lineare Funktion. It's more or less a linear function that has been transposed and put away or into a certain direction from the 0. Ja. Auch nochmal kurz auf Deutsch, weil mir das schon wichtig ist. Das ist halt in der Mathematik und in der BWL, VWL ein bisschen anders. In der BWL, in den Wirtschaftswissenschaften schwafeln wir halt gerne und reden irgendwie von linearen Funktionen. Und es ist klar, dass f von x gleich a plus bx, das ist eine lineare Gerade, das ist natürlich das, was man üblicherweise als lineare Funktion betrachten würde. Aber in der Mathematik ist ziemlich klar, eine lineare Funktion ist eine Funktion, die die Regeln des Vektorraumes erfüllt. Und ein Vektorraum ist halt definiert über die Vektoraddition und die Skalarmultiplikation. Also ein Vektor ist dementsprechend hier ein Objekt V und ein Objekt W. Wenn ich die beiden addieren kann, ich habe wieder ein Element des Raumes, dann habe ich die Vektoraddition. Und wenn ich den Vektor V nehmen kann und strecken oder dehnen kann mit einem Skalar A, dann, und das Ganze bleibt auch innerhalb des Raumes, dann ist eine Skalarmultiplikation und dann ist die Funktion f linear. Das definiert aber dann natürlich oder bedingt, dass alle Vektoren zwangsläufig durch den Ursprung gehen müssen. So. Und wenn ich so einen Vektor jetzt nehme und ich ziehe den aus dem Ursprung raus und verschiebe ihn im Raum, habe ich eine affin-lineare Funktion, dann auch in der Geometrie, aber in der linearen Algebra wäre das halt nicht mehr eine rein lineare Funktion. Wir sprechen also hier bei der linearen Optimierung üblicherweise von affin-linearen Zielfunktionen und affin-linearen Nebenbedingungen. Such a linear optimization problem is also called a linear program, or in short LP problem. You probably have not seen this in your math education in the first year. This is used heavily in what we call operations research, but also in optimization when it comes to supply chain management and production management. It's quite nice because we have a very strong and very powerful algorithm to solve such a problem. That's the simplex algorithm that dates back to, I think, the 40s or 50s. With the linear programming, it's quite easy to show that, to solve for the solution of a linear program. Problem is that in practical applications, we are dealing usually with a very large objective function and hundreds and sometimes thousands of linear constraints that make it very tedious to solve for this solution and to solve this problem. Yeah? But the simplex algorithm is quite powerful. And then we have continuous versus discrete and stochastic versus deterministic optimization. If the solution set is restricted to the set of discrete whole numbers, we will get a discrete optimization problem in contrast to a continuous problem. And if we have stochastic objective functions and stochastic decision variables, you will get stochastic programming and stochastic optimization. Stochastic optimization is something that is very tricky and where nowadays a lot of research is done. Even though we should consider this a stochastic program and stochastic optimization problem, the decision variables, they are more or less random variables. However, in our simple setting here, where we take the expected return and the volatilities of the stocks as deterministic givens, we can stick to deterministic optimization, and we do not need the much more difficult methods from stochastic optimization, but there is such a thing that deals with stochastic optimization problems. And discrete problems, this is again quite interesting. One would think that if you reduce the number of possible solutions by taking, instead of the real numbers, the discrete numbers, This would simplify optimization, but in fact it makes optimization a hellish endeavor, and it creates a lot of problems because you cannot simply buy 1.5 stock. You cannot buy 2.3 stocks, and you cannot produce 2.3 cars, but you can only produce 2 or 3 cars, and then this makes optimization quite difficult. Okay. So these were some basic general remarks concerning optimization, and we'll now turn to unconstrained optimization, and I'll have to switch the set of slides now. Wie viel Zeit habe ich denn noch? 25 Minuten, dann machen wir auf jeden Fall noch was. Just open the next set. Okay, we'll start with the basic case of unconstrained optimization. Most approaches for determining numerically the local optima, they are usually iterative. So you'll use a sequence of solutions that should give you better and better function values, smaller function values if you're minimizing. And the sequence of solutions should converge ideally to the solution we are looking for x star. So we'll only consider minimization problems, and in order for the sequence to run in the direction of a local optimum, for each entry x, xk, we need to find a descent direction. The idea is very simple. Think of this floor here as the function graph. And what I'm trying now is to find the minimum of this function graph. What I could do is I could take like a ball, I could just throw it down to the floor, and I could try to look at where the ball rolls. It rolls into, obviously, the direction of steepest descent. And then the idea behind all of these algorithms is that I should take the next solution and I should go into the direction of steepest descent, where the function decreases at the highest rate. And it's quite simple to find this direction of steepest descent. You simply take the gradient, where the gradient becomes minimal. So we are trying to find a vector S so that the following holds. F, the function value of the next solution, xk, our current solution, plus alpha times S, should be smaller than the previous function value. So this is where we start at, and we want to improve this solution, xk. So we take xk and we go into the direction of steepest descent. S, that's the direction. And the question now is, should we take one step? Should we take 2 steps in this direction? And this is what alpha is. So alpha is the step length, and S is the step direction. So we're assuming the step length alpha in the direction S from xk, and we hopefully get a minimization of the previous function value f of xk. Now if we write the function h alpha equals f of x plus alpha s, then a descent direction is characterized by what? We want the derivative of h with respect to alpha at alpha, that is the transposed gradient of of f times s, to be smaller than the 0. So it should be a direction where the function value decreases if we go in the direction of s. If necessary, sometimes we need to normalize the descent vector to the length of s by using the norm of s. Then a simple optimization algorithm could look like this. We need to find the descent direction, S. We need to find the step length. We will update our current solution as xk by taking xk plus alpha step length into direction S, and then we abort as soon as we think that we found the best solution. So after a couple of steps or after some kind of convergence criterion is fulfilled. Now, such an optimization algorithm will not necessarily find a global optimum. Even with this very simple picture, this very simple image of me taking a ball, letting a ball fall to the ground and the ball flowing and going into the direction of the steepest descent, this makes it very simple to see that we can only find a local optimum by this. With the convex problems, we know that we only need to find a local optimum because the local optimum will already be the global optimum. With all other functions, well, we cannot know. What you can do then is, because there is no way to show that an optimization algorithm is better or worse than any other given optimization algorithm, you can use those optimizers on test functions. And with the help of these test functions, you can then check whether an optimizer is able to find the known or approximately known optima of these functions. And to show you and to give you an idea of what these test functions look like, I've now compiled a list of a couple of test functions. For example, the Ackley function. It's an n-dimensional real function, and you can see it's defined by minus 20 times the exponential function here, minus exponential function, plus 20, plus exponential function again. It has a global minimum at 0 and numerous local minima. Bird function, also very simple, two-dimensional function. A Booth function. This is really simple. As you can see, this is a polynomial. And it has a global minimum in the point 1,3 and numerous local minima. And the Schwefel function. Again, one global minimum, several local minima. And this is the Ackley function. As you can see, this looks like a very simple function. Actually, the definition also looks very simple, but you have numerous local minima, and you simply cannot see them. Then the Bird function looks a little bit more unpleasant, as you can already see some of the local minima. The Booth function is rather tricky because I've plotted the Booth function from different angles. And as you can see, there is nowhere to tell where the global minimum is. And actually you cannot see the local minima. And well, this is self-explanatory. The Schwefel function, it's quite simple to see that it has numerous local minima and maxima. And by applying any optimizing algorithm to these test functions, you can see how they would perform in a worst case scenario, because these test functions obviously constitute a worst case scenario. And if they perform well, then you know your optimizer is good. Okay. So we'll start with a gradient-based method. With a gradient-based method, also called the method of steepest descent, you set the step direction by taking minus the gradient divided by the norm of the gradient. The step length, alpha, can be computed by solving a one-dimensional problem. You take the function h of alpha, that is defined as the function fx xk plus alpha times the step direction, and you first compute the step direction by taking the gradient. Then sk is calculated, you insert it here and sk is fixed. xk, your starting value, is fixed. So this here, this function h, only depends on alpha, and this is a one-dimensional optimization problem. So you calculate the step direction, you take the gradient, then you do a one-dimensional optimization to calculate the step direction, the step length, and you repeat the whole process. To put it more visually, you start at this point here, you calculate the gradient, and then you know that you have to go into this direction. The question now is, should I take 1, 2, or 3 steps? And this is only a one-dimensional problem and optimization problem, and this is very simple to solve in each step, in each iteration of the algorithm. This is called the gradient method, Gradientenmethode oder Gradientenabstiegsmethode. If you simply take xk plus 1 equal to xk minus alpha k times the gradient normalized. It converges comparatively slowly and relatively poorly near local minima, but you only need the gradient as an input variable. Now, the gradient method obviously has the disadvantage that you need the partial derivatives, and thus it can only be applied to differentiable functions. In the vicinity of the optimum, the convergence speed is relatively small, and you sometimes have zigzagging. What is meant by zigzagging? It means that, for example, if this is the optimum, and you start here, and then you find a point here and here, that you do not converge like this, but you converge like this. And you have zigzagging between the optimum. And the number of iterations increases, even though the accuracy of your solution is not improved by much. And formally, the comparatively poor convergence of the gradient method is due to the fact that you're using a first-order approximation. This is a first-order Newton approximation, and you're only using the first derivative. In many cases, the use of a second-order approximation might yield better results. And an example for such a method is the Newton method. That's the second algorithm we want to look at. If instead of the gradient method you use and you approximate f x plus delta by fx plus the transposed gradient times delta plus half of the delta transposed times the Hess matrix times delta, you will get a better approximation to the target function. And then you can calculate the iteration from this. The Hess matrix is what? Who remembers this? Was ist die Hesse-Matrix? Ist die Matrix der zweiten Ableitung einer mehrdimensionalen reellen Funktion. Also alle partiellen Ableitungen und natürlich dann die Ableitung nach einer Variable zweimal. Also das, was die erste und die zweite Ableitung bei einer eindimensionalen Funktion ist, ist der Gradient bzw. die Hesse-Matrix dann im mehrdimensionalen. Deswegen haben Sie dann hier, also auf der Diagonalen natürlich die zweiten Ableitung und hier dann immer dann entsprechend die Kreuzableitung, ne, nach x1, x2, x1, x3 und so weiter. Das ist jetzt die Matrix. Okay. If h is positive definite, this means symmetrical, and x times h times x is larger than 0 for all vectors x unequal to the 0 vector, then f is locally strictly convex and minimizing the Taylor approximation of f returns a minimum of f. And this is equivalent to using the Newton-Raphson algorithm we've already seen in one dimension on the necessary condition that the gradient should be equal to the 0 vector. So this is the Newton method. You can see you are not simply using the gradient, the normalized gradient now, but you're using the gradient and the Hess matrix. You're using additional information from the curvature of the function, that is the second derivatives of the function. So xk minus alpha times the inverse of the Hess matrix times the gradient, and it shares the convergence properties of the Newton-Raphson algorithm. It's quadratic and thus quite fast, but requires the evaluation of the Hess matrix and the gradient in each step. What does it mean? Remember two things. We can distinguish between the convergence speed and the overall speed of an algorithm. What does it mean? Convergence speed means that, for example, I'm looking for this solution S here, and convergence speed means I need to use 1, 2, 3, 4, 5 iterations. I is equal to 5, or K is this K star is equal to 5. If we have a second algorithm that needs 1, 2, 3, 4, 5, 6, 7, 8, maybe in a different order, hopefully. Let me just get this. That requires a number of iterations like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The second algorithm has a worse convergence speed. However, if the two algorithms differ in the amount of time needed in every iteration to calculate the next iteration, the second algorithm could still be faster. So if we need 1 minute, 1 minute here, 1 minute, and 1 minute, and 1 minute, this means we have 5 minutes overall speed and time needed for algorithm 1. If this here has a worse convergence speed, but each iteration is calculated much faster, it might be that if it only needs 1 second, we will have a tremendous difference in speed, even though the convergence speed of the algorithm is better for the first algorithm. And here it's quite simple to see this. The gradient method needs what? The gradient in each step. The Newton method needs the gradient and the Hess matrix in each iteration. So we have more computations in each step, in each iteration. And in this case, it might be that the Newton method is faster because the convergence speed is higher, but it could also be that actually the gradient method is better because even though the convergence speed is worse, we do not need to evaluate the Hess matrix in each step. In German, again, ganz einfach zu sehen. Wenn ich in jedem Schritt bei der Gradientenabstiegsmethode nur die ersten Ableitungen bilden muss und da Zahlen einsetzen muss, habe ich natürlich weniger elementare Rechenoperationen, als wenn ich noch in jeder Iteration zusätzlich noch die zweiten Ableitungen bilden muss. Die muss ich auch immer wieder bilden und muss da die Zahlen einsetzen. Und dann rechne ich mich eventuell am Ende in der zweiten Methode, die zwar schneller konvergiert, einfach zu Tode, weil ich da den Computer die ganze Zeit nur irgendwie Zahlen in Funktionen einsetzen lasse. Und die höhere Konvergenz, schnellere Konvergenz des Verfahrens nutzt mir eventuell gar nichts, weil ich viel mehr Auswertungen vornehmen muss. Aber das kann man nicht vorab sagen. Es kommt drauf an. Okay. Now these were gradient-based and derivative-based methods. Frag nochmal, wie viele Minuten habe ich noch? 7. Ah, wunderbar. Danke. So these were derivative-based methods. In some cases, you will not have differentiable functions. And in some cases, you will not have functions at all. How can that be? Quite simple. In many cases, you will not have a function to minimize, but you only have a set of numbers, a set of function values, you know have originated from an unknown function f. And this is actually often the case in social sciences. If I were to calculate, and if I were to maximize a price function from marketing, or minimize a price function, in any case, I'm interested in a price function. Do I know the price function? No, I can only ask people, how much are you willing to pay for this product? Then I will have 100 data points, and these 100 data points are function values of the unknown price function, and I can then assume a certain functional form for the price function. I can approximate a function with these points, but the function is not known. And if it's not known, if it only originated from discrete values, well, it usually is not differentiable. So we need derivative-free methods for optimization in case we know, or we have to assume that we cannot calculate the derivatives of the function. So this is a disadvantage of both the gradient and the Newton method. You need the function to be differentiable. If this is not the case, you need derivative-free methods. So sometimes you also have jump points, Sprungstellen. So in order to avoid these problems, we need derivative-free methods. And one example for such a derivative-free method is the simplex algorithm by Nelder-Mead. The Nelder-Mead algorithm. This is a very simple one. This is a heuristic optimization algorithm, actually. The idea is very simple. The idea is you use a set of solutions, x1, x2, x3, say x5. You check for the function values of these solutions, and then you see that this is the best and this is the worst solution. What you do now is you delete x2 and you insert a new possible solution, x6. And how would you do this? Well, the Nelder-Mead algorithm gives you some ideas how to construct a new possible solution, x6, that you will insert in this vector. For example, by combining the best and the second best solution. So you could say, okay, I take 0.5 times x3 plus 0.5 times x1. This gives you x6, and then it's an iterative method. You repeat the whole process. You insert the new point in the set of solutions. Now, which point is the best? Which point is the worst? Eliminate the worst one, insert a new solution, and repeat and repeat and repeat until something happens. And it's called a simplex algorithm because geometrically you're using a simplex. Simplex in German ist ein konvexes Polyeder. Also so etwas. Das ist ein konvexes Polyeder. Ein Vieleck, das konvex ist. So etwas, das ist kein konvexes Polyeder, weil man sieht, die Verbindung aus zwei Punkten wäre nicht mehr in der geometrischen Form, also es ist nicht konvex. Gut. Wieder was dazugelernt. And the idea of this simplex algorithm is to evaluate the target function at n plus 1 different points, exclude the worst points, and replace it with a new point. And this new point is determined by mirroring it at the center of gravity of the simplex of the remaining points. How do you do this? Actually, this is a very bad example. You need more points for this. Assume that you have points here. And you have this point here. You see this is the simplex. Now, these are only the possible x values. From this graph, I cannot tell whether this point is the best or not. It could also be that this point is the worst solution at this point. Now assume that this is the worst solution. What I'm doing is I'm taking the remaining points, taking the simplex, the point of the gravity point of this would probably somewhere be here, and then I'm mirroring it to here, and this now is my new solution. Okay, if this is the new solution, I delete my old one here. Okay, then if in these points this is now the worst solution, what do we do then is we calculate the convex polyeder, the simplex of the remaining points. Then the point of gravity of this simplex is probably here. Again, mirror it. And this is the new point. Delete this point. And this is how you repeat each iteration after iteration. And that's the nail-the-meat algorithm in a nutshell. I hope I described it correctly. Yeah? Okay. Our colleague from the math department here says it's okay. But I'm actually quite proud of myself because, as you can see, this works much, much better with more points than just 3 points. Because with 3 points, it will be a triangle, and it will not really be an obvious simplex. Yeah. I'm being told, yeah, that my time is, I'm running out of time. You can look through the algorithm, the iteration sequence for the nail-the-meat algorithm on your own. We'll discuss it shortly next week, but as you can see, it's basically just this. Take the set of solutions, identify and sort the set of solutions according to which solution gives you the best and the worst result, eliminate the worst result, construct the new point, insert it into the vector, repeat, 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 and then fine-tune it. As you can see, calculate the point as a center of gravity in one dimension, calculate the mirrored point. If the returns a better function, then do this, otherwise repeat. If the new point is the best value so far, it is a tuned algorithm. Why? What I lacked, or what I leave out here is, obviously, if this new point is so good that it's already the best point so far, well, why stop there? You can go even one step further. So then, if you see, okay, this is the new point here, well, but this suddenly now is the best solution we have in the whole set of solutions, well, then let's go into this direction even more. And this is why we do not have one simple step here, but if the new point is the best value so far, calculate the extended point. At this point, we have calculated the contracted point, go a little bit back. This is the fine-tuning of the algorithm. It's not just always calculate the mirrored point, den gespiegelten Punkt, but also if suddenly the new solution is so much better, go even further. If it's worse, go back, contract it. That's the same here again. So if this new solution is even worse, then maybe just go like this, or even go into the other direction here. So this will give you the additional steps of the nail-the-meat algorithm. And as you can see, we have some parameter values here, alpha, gamma, rho, and sigma. And these are some common starting values for these parameters that give you information on how much you should go into the direction of the best value, by how much you should contract this point, and so on. But the nice thing here with this nail-the-meat algorithm is you don't need anything. You don't need any derivative. You don't need the function. You only need a set of function values x and f of x. And then you can start your optimization. And this is a derivative-free algorithm. Okay. So I'll stop here. You can have a look at the Nelder-Mead algorithm at home again. And if you don't have any questions, thank you for your attention and see you next week. Thank you.